Hey, good morning, folks. Let's see if we've got any familiar faces here. Great, we got Dawn and Brian, Ellen, good to see you guys. Some names that I don't know, which is great. Every week we've got some new folks joining us. Megan, hello Megan, good morning. Okay, fantastic. Okay, it looks like actually today I kicked everyone in pretty quickly. So I think with that, we'll just go ahead and get started. Today, I'm really pleased to have a bit of a special guest join us this morning. We have Dorta Koster, who is the board chair of the Alberta Lake Management Society. Dorta, I actually think I will stop sharing, but I will pass it over to you to say a few words if you like.
Yeah, good morning, everybody. Welcome to our last session here on the ALMS webinar series. I really would like to thank everybody for participating. We have had a lot of really good discussions here. I'm very happy that we were able to have some kind of venue to exchange knowledge. We usually meet in person, and we all miss that very much, and we hope to do that again over the next years. But yeah, this is what it is, and it opened up our opportunity to invite people from all over, which was very yeah, very yeah, educating for sure. We had so many good perspectives in this series. So I want to make a big shout out to Brad here, who's been organizing the seminar, finding good people like for his relationships and his networks. He has brought in really an excellent diversity of speakers. So thanks to you. And yeah, I hope you all enjoyed it and still enjoy the talk today. And yeah, Brad here will give us a little brief overview of ALMS as well, so you know what we're about. And I hope you can maybe join us at our AGM or at some events that we're going to be putting on in the future. Thanks.
Great, thanks, Dorta. Okay, so for those of you who aren't from Alberta or from Edmonton, just a couple comments about the programs that we do run. We strive to improve our understanding of lakes and reservoirs and their watersheds in all the work that we do. And we had a really successful year with Lake Watch. This year, we had 105 sampling trips completed by our staff. They did a great job. We had 105 trips planned and we had 105 trips completed. So a fantastic season for us in Lake Watch, and it happens to be our 25th anniversary year as well. So despite the challenges in the world right now, I think we've been really lucky that we're able to keep up the great work that we're doing through Lake Watch. As well, our Summer Lake Keeper program is just about wrapped up. This is our more traditional citizen science program. We will be running a winter program as well this year. So if you're interested in getting involved with the winter sampling, we will be hosting a winter training session probably in November this year and get started with sampling in December. So I hope if you're interested, if you're an angler here in the province, this is a great program for you to get involved in. So do reach out if you have any questions about that. I'll mention too that our annual scholarship was awarded to Ferris from the University of Calgary for her work on winter linology. So if you're a grad student or prospective grad student watching today, I encourage you to check out our scholarship page on our website. The next scholarship should be posted next spring, and it's awarded to undergraduate students or graduate students studying topics related to ALMS mission and objectives on lakes. So I encourage you to reach to apply. It's a great little scholarship, and I'm looking forward to hearing more about Ferris's research, hopefully at our AGM in November. And I can say that the board has selected a date for the annual general meeting, which will be November 25th. This will be virtual likely, but I hope you'll be able to join us at our AGM. So I will stop sharing and start today's session. So for those who don't know me, I'm the executive director here at the Alberta Lake Management Society, and I'm joined today by Caleb, our program manager, who's going to help facilitate today's session. The Alberta Lake Management Society is based in Edmonton in Treaty 6 territory, and this is also within the Métis Homelands and Métis Nation of Alberta Region 4. And the second session in today's webinar will be talking about Pigeon Lake, which also happens to fall within the same traditional territory. If you weren't able to join us last week, we had 2 great sessions, and those are now available on our webinar page, and you can find them on YouTube as well. I hope you've enjoyed the session so far. If you've missed any of the previous sessions, they're all up on that webinar page or YouTube page. And today's session is being recorded. If you have any questions during the session, please submit them through the Q&A function at the bottom of your screen. It's harder for us to track the questions in the chat, but we can definitely follow them in the Q&A function. If you submit a question during today's webinar, as with our previous webinars, we will enter you into a bit of a draw for a bit of a prize. And today's prize, we've tried to make them relevant to the speakers. And so today we're giving away a copy of, oh, you can't see it, it's blurred. I'll have to turn my blur off because I would love to show you the nice cover. Let's see if I can do that really quick here. See how savvy I am with this video business. You know what? I'm not savvy enough. I don't think I can do it. But we are giving away a copy of Internal Phosphorus Loading in Lakes. And this is Causes, Case Studies, and Management. And I'm really excited to be giving this away because it's a great resource, but also our first speaker, Gertrud, contributed multiple chapters to this book. So, so I really hope whoever wins it takes a look through it. It's been a great resource for us at the Alberta Lake Management Society. So without further ado, our first speaker is Dr. Gertrud Nurnberg, and she's the head of freshwater research, a limnological company focused on restoration and modeling of eutrophic lakes and reservoirs. Gertrud founded this company in 1984 after completing her PhD in limnology at McGill University. Gertrud is really well respected in the limnology community. She's won the NALM Secchi Disc Award, Technical Excellence Award, the Best Paper Award, all in recognition of the great research that she's been doing. So I've been really fortunate to attend Gertrud's internal phosphorus loading workshop at NALM's conferences, and she's been running those since 2003. NALM's is going online this year. I don't know yet what the situation is with the workshops, but if you ever get a chance to take Gertrud's workshop, I would really recommend it. So Gertrud, thank you so much for joining us today and agreeing to be here today. I'll let you share your screen now and pass it over to you. Let's see if we can get the screen sharing to work here. So that looks fantastic.
All right, very good.
Great.
Well, thank you very much, Bradley. That's a very nice introduction. I must say, I really did enjoy your previous, the webinars. I think what a great idea. And also, especially in September, after we were swimming in, in all summer in the lakes, now it's about time to do some theory. And I was just so impressed how many programs you guys have in Alberta. I mean, by people, it's such a small province, no offense, compared to Ontario, and I barely know that many things going on in Ontario. It's just amazing. So thank you very much for giving me an opportunity to contribute to this great endeavor here. I want to acknowledge, I mean, thanks for Brad and you guys, but I also want to thank my husband, Bruce Lizard, who really is a partner of Freshwater and Research and Life. And we have lots of discussions over dinner table on various lakes and issues and stuff like that. The participants of NELMS, especially of the internal load workshops that Brad was talking about, all these questions and comments help me to sort out things, what is important and what is not, and how things are still different in different locations, different times, and so on. Then the lake groups that asked for help. I mean, since I'm not in academia, I could get some grants, but many of the smaller projects were funded by small little lake groups or that got funding somewhere. And they really broadened my horizon again to look at on the ground problems. And I don't want to forget the First Nations and indigenous peoples that occupied the lands of the various studies. They are all over Canada, some in the States and also Europe, but that's a different story then. So although I will talk about internal load, I want to talk about the interactions and maybe the influences of internal load on cyanobacteria blooms. Now, those blooms have been reported for a long time. Look at Pine Lake, the lake you know in Alberta. In 1990, Al Sozak gave me this photograph a long time ago, and it wasn't until external as well as internal sources and treatments had been incorporated that the lake actually, the water quality got better. So I will do a little bit more formal and talk about hypotheses, because although often people assume that internal load and cyanobacteria are related, it's not really that well documented. So cyanobacteria and blooms are often caused by phosphorus released from lake bottom sediments, is hypothesis number one. And then recent increases in such blooms are partially caused by increases in internal load during climate change. There are many reviews, meta-analysis, and some of them, the more recent ones do acknowledge some internal load possibilities, but the earlier ones did not. So in this 45 minutes, if I have them, I will come back to the hypothesis from time to time. I will talk and explain how I see the eutrophication process with respect to the phosphorus cycle. I talk about the internal load, characterization it as oxygen-related sediment release. That's the main source, and also the importance of quantification rather than just saying, okay, there is some internal load, and cyanobacteria is the main subject then, and internal load during climate change. I have a few slides for that and some indications. So how I see and how many people see the phosphorus mass balance is kind of, the phosphorus is kind of the currency of water quality. So if you have a lot of it, you probably have bad water quality. So, and the sources are external load with all these well-known possible sources. And then you do the whole budget by monitoring the outflow to arrive at the P export. Now, what happens in the lake is not so easy to distinguish from another, because phosphorus settles sedimentation And there is, when we do have internal load, there is something coming up. So this here was often just determined or named retention based on these two measured variables. And what I have been doing actually since my PhD is trying to predict or calculate this internal load. By one way of doing it is by knowing a model that separates the sedimentation out of it, which is based on the QS, which is annual water load. And then there are other ways, and I'll show you some how to arrive at internal load. So how I envision the eutrophication process is under natural conditions. Hopefully the lake has some external load. It will always have external load just coming from natural sources, but there is no accumulation and no conditions in the sediment, close to the sediment, to have sediment release. Then you have urbanization, or you have anthropogenic development, you have stresses, agriculture, and the external load increases tremendously. And not long after that, you will have conditions that allow for phosphorus release. You have accumulation here, and you have changes in the conditions. Then, since we realize wastewater treatment plants are necessary and BMPs and so on, the external load is being decreased, and so you really feel the phosphorus in the lake should also decrease, but it has not because of the internal load that's still there. And that happened about in the 70s, 80s, and 90s, and that's when internal load became all of a sudden a very important thing to study. And then what we really want is kind of a normal, natural external load and as little internal load as possible. And we arrived at that by in-lake restoration or internal load treatment. Just for those people who don't know exactly also what is the sizes, the external load can be as large as the internal load or vice versa. The internal load can be even larger than external load. It all depends if we had already wastewater treatment or not. In case external load can be very low because of wastewater treatment, like here, but internal load is higher and the other way around. That's just to give you an impression. So back to the theory of sediment phosphorus release, just as Ken Wegner in his restoration webinar last week mentioned too. The geochemical processes are probably, and I found always the most important ones quantitatively. And what is happening here, it's a geochemical process where the iron oxyhydroxides release the adsorbed phosphate when they become anoxic or low redox. That's why it's called a redox-related process. So that means it's important to have dissolved oxygen, anoxia, and redox potential. You want to know how they are, what they are at the sediment surface, sediment water interface. The importance of temperature and thermal mixing state becomes evident as well, because the higher the temperature, the faster these processes occur. And also the mixing state will determine where the phosphorus goes. Does it get mixed right away into the whole lake or only stays in the hyperlimnic, the bottom water? And then it has an importance of the trophic state, the degree of eutrophication. I have some examples later. Less important, I have found, although it has been studied, bacteria mineralization in very high hypereutrophic lakes. That might be a reason, and more important. Macrobenthos biotubation can actually go both ways. Some can absorb phosphorus, and senescing macrophytes. So if we have a situation like that, and I explain in a minute, you can be pretty sure it's internal load, and it's probably a redox-related internal load. Now, this is based on an oligotrophic lake. Look at the concentrations of phosphorus. These are profiles, this is microgram this way, and that's the depth. The phosphorus concentration is less than 10, and it increases with depth. The phosphate, which is measured as soluble reactive phosphorus, also follows this parallel. It's 0 in the top, and it increases with depth. At the same time, if you look at the oxygen, it decreases, and it's anoxic at depth. And at the same time, you have the iron, all sorts of analyzed iron, total iron soluble, and even the reduced iron, Fe2 plus, are increased. So that's a typical redox-related phosphorus release. So it is interesting to know, and this is now a plot from very many grab samples, so to say, from hyperlimnic anoxic waters in several lakes, I think 15 lakes or so. It is interesting to see that the total phosphorus, when the total phosphorus is like 100 or higher, the SRP is getting almost as high as the total phosphorus. And that's what we expect, because SRP is a kind of phosphate, and the geochemical process liberates phosphate. So, but it also means if you do see a lake that's stratified and had elevated phosphorus in the bottom, and you can only measure total phosphorus, most of it is probably phosphate. But in a polymictic lake, this is now differently. How can you find out internal load in a polymictic lakes where you don't have the separation between the bottom water, the hyperlimnian, and the epilimnian, the surface water? So look at this lake in semi-arid South Dakota. You have a spring freshet or high spring flow with a high external load. 99% in this reservoir came through the main inflow. It can easily be measured, and then nothing anymore. At the same time, the lake phosphorus concentration is quite high already, 300 microgram per liter, about 0.3 milligram per liter, and it increases throughout the summer. So since there is no precipitation and there is no inflow, where would it come from? It must be an internal source. So if we have a situation like this, you can directly calculate internal load from the increases from the summer, early summer to late summer and fall. And that I usually refer to as in situ estimate of internal load. Now, in this case, you have a mesotrophic lake, which is oligomictic, which means in some years it behaves like a stratified lake. This is microgram per liter phosphorus for 3 years, 3 summer seasons. And in this year, you can see that it was stratified until almost fall, and then the red is the phosphate. And then it turned over. In this year, it was stratified until, let's say, beginning August, and then it turned over. And here in this year, it seemed to be the thermocline erosion, that's what it's called, happens during the whole summer, so that here really behaves like a polymictic lake. So in terms of our hypothesis, I also plotted the chlorophyll concentrations, and they are following and correlated to the phosphorus and follow this pattern exactly. And if you have that, you not only think it's internal load that increases the phosphorus, but also that phosphorus would have an effect on the chlorophyll, and the chlorophyll is, in this case, mainly Cyanobacteria. So to kind of summarize, the elevated phosphorus from the anoxic hyperlimnin is highly bioavailable and can fertilize phosphorus deficient plankton when in contact. In polymictic shallow lakes, it's not so obvious. You really have to look closely. Throughout the summer and fall, you would have an increase though. And in stratified lakes, you have the thermocline erosion, then you have metalimnetic mixing, you have fall turnover, and then you have elevated phosphorus concentrations. Now, the hypothesis supporting evidence is that that at the same time, correlated to phosphorus, you also have increases of chlorophyll. And again, it's the same kind of pattern as the phosphorus temporal pattern. But there are real examples. One, not in your next province down, probably lakes, you might have similar lakes. This is from Peter Levitt's lab in Saskatchewan. In this lake, the phosphorus clearly increases here. It's from April to October. This is phosphorus, dissolved phosphorus, because the lake is polymictic and also phosphate. Total phosphorus would probably not indicate anything available phosphorus. So you see the increase in August. The maximums might be August or between July and September, depending on what you use here. And at the same time, the Cyanobacteria, which are above that green here, are also at maximum. The percentage of the whole phytoplankton that is Cyanobacteria. So again, that would be a supporting evidence. Some more time I want to spend on this lake here, Lake Simcoe, Southern Ontario, which is a mesotrophic lake. And it has a stratified bay, Kempenfeld Bay, while the rest is kind of very well mixed. I mean, more or less mixed, I should say. And the Cook's Bay sometimes stratifies too. So I did a study separately for all the three basins, but or sections, but I show you now for Kempenfeld Bay, the stratified season. You see here that these are Cyanobacteria biomass, and these are years, and these are months. So you see that in the highest concentrations of the Cyanobacteria, which were mainly Dolichospermum and Aphanizomenon, are in late summer and fall, all in this type. You can also see that something happened here, and this is decreased after 1992. So the temporal pattern alone from seasonal pattern, again, would support internal load if there is any. And yes, there is some. I just want to go through this here. By looking at separate years averages, you see that the Cyanobacteria first significantly decreased from the first several years to the next group of years. Then you see the hypoxia also decreased, and the hypoxia was calculated from actually profiles. Then the in situ internal load, like the increases over the summer, also decreased, although this is kind of overlapping and it's not significant because of the large variation of the in situ load after in the second group of years. And the release, another estimate of internal load, which I explain in a minute, is also shows decreases. So the pattern, this here is based on hypoxia and release rate. So it all is kind of supporting the possibility that actually internal load has an effect that the cyanobacteria are less now because internal loads seem to have decreased. So in terms of spatial and temporal extent of hypoxia is correlated with cyanobacteria biomass. I just pointed out here in Lake Simcoe that the hypoxia is related to internal load because enriched sediments release phosphorus when the sediment-water interface is anoxic, and which is another way then to estimate internal load. And this is the other way. If you have, if you as I see it, you can look at internal loading from two ways. You can first look at the release rate. How high is the release rate for an area that can release, like an anoxic square meter? So it would be the release rate of phosphorus in milligram per meter square of anoxic or active area per day. But then with the units properly done, and you can multiply this by the actually area in time and space that is active and is anoxic. And that can be calculated from oxygen profiles. But so in stratified lakes, you will be able to calculate it right away, determine it from the actually monitored data. But in polymictic lakes, you would not be able to do that because of wind mixing and mixing. The sediment would be able to release stuff, even though the overlying water might have some oxygen in it. So here you use a model because it's related to phosphorus and morphometry, and so you can still arrive at an internal load in polymictic lakes. For example, the release rate per anoxic area has been found to be strongly related to total phosphorus concentrations in the sediment and in the lake water, kind of, but the trophic state, it's quite convincing. Now, another lake, you know, Lake Winnipeg in Manitoba is notorious. It's been voted one of the worst lakes, Canadian worst lakes in 2010 because of the blooms. And as you know, it has a huge watershed. So would internal load have anything to do there at all? Just to refresh you, Lake Winnipeg gets the main phosphorus load from the south, even though the rivers are not giving that much water load. So you have the South Basin, the Narrows, and then the North Basin. And the Saskatchewan River actually dilutes the phosphorus there because it's in better shape, less phosphorus than the lake has. And there is a phosphorus trend also with highest phosphorus concentrations at the South Basin, leaving some in the Narrows and less in North Basin, and then it goes out into the Arctic Ocean. So I did the internal loads for all these three different basins, and then I got them together to come up with an internal load for the whole lake. And you see here, this looks very much variable. There's variation. Let's look at what we know best first. It's the in situ load. Usually an in situ, like an increase from during the summer, is lower than any other estimates because some settling has already happened. But and it is the case here if you compare it to the other ones. Green are mass balance related estimates, and this is extended with a regression, the orange one here. Purple is what I was saying by using a model for the active area and a release rate based on 2 different ways of predicting the release rates. So they provide different estimates for different years. And to make a long story short, though, if you compare it all together and take averages and so on, the internal load is still at least as high as the external load, which is the black one. I want to impress on here that it is important to actually calculate things, even if it gets so messy as it is here. You see, it was never calculated as zero, and many people do not think that a lake which has so much external loading could have internal load at all. So it is important to also then you can do differences with climate conditions and so on, if you have estimates for each year. Now back to the hypothesis in Lake Winnipeg, the chlorophyll concentrations, there are not many data for this large lake on chlorophyll and almost none on phytoplankton, at least not back then. So this was correlated to the South Basin phosphorus under ice. It might be a stretch, but phosphorus under ice, when it's variable like that, is likely correlated due to internal loading, possible anyways. And it could be that the following season, July, October chlorophyll concentration that is related to it as an estimate, maybe due to sediment released phosphorus. There are some more direct relationships, not very good, just barely significant, for internal load in the North Basin, correlated to the chlorophyll in north and the whole lake and cyanobacteria in the south. I think this will all have to be done with better data, especially on the phytoplankton. Mainly, very often, the phytoplankton data used to be missing. Okay, now the reduction of cyanobacteria after internal load abatement and lake restoration. Now this is often in lake restoration people, it's often assumed quietly that an in-lake restoration program that deals with internal loading actually will also take care of cyanobacteria. But here I want to just stress on that it's actually, really the case. I think this hypothesis can be supported by the statement. First, I look at hyperlimnic withdrawal and then at some chemical absorption. Hyperlimnic withdrawal, and I know Ken was talking about it, Ken Wegner last time. You dam the inflow and instead withdraw water from the bottom. You can only do this in stratified lakes. So you withdraw basically the sediment released phosphorus and other substances that you don't really not good in a lake, like hydrogen sulfide, for example, and you send it downstream. There are several in North America, just 9 known treatments, but in Europe, it's being used more often. There are all sorts of sizes. The lakes have to be stratified, otherwise it doesn't work. And here this actually shows that in this data for 11 lakes and also supported by 3 more lakes, that the aerial export of total phosphorus during hyperlimnic withdrawal actually is so correlated, significantly correlated to the change in total phosphorus in the lake, that we kind of can be certain that hyperlimnic withdrawal actually does something to the hyperlimnic water phosphorus concentration, which is, internal load. So if at the same time, if also the cyanobacteria then decrease, we could say that is due to internal load decrease. And there are several incidences where this is the case, especially for the metalimnetic Planctotrix rubescens bacteria. This is now an old study from a Slovenian lake. You see here the Planctotrix, used to be Oscillatoria called, in white, decreased with hyperlimnic withdrawal. And this is just one graph, but there are other situations where it's been shown, especially for Planctotrix, hyperlimnic withdrawal decreased or made the problem of the cyanos go away. And the idea is it's because the cyanobacteria go to the bottom, these ones. They are low light adapted, they are usually at the metalimnion. They get, they sit at the metalimnion or migrate a little bit around it and get the phosphorus that is from the internal loading, and that supports them. However, also surface blooms are can be treated with this method. And here is another slide by Sosiak on Pine Lake. And you see here quite convincing a decrease in the chlorophyll, which was mainly cyanobacteria in 3 basins. And he also said that. Further, Secchi transparency during hyperlimnic withdrawal increase in 19 out of 21 lakes. Another indication that hyperlimnic withdrawal, which withdraws internal load, also helps cyanobacteria. And so to further support this hypothesis, I just looked at a chemical precipitation. Alum, for example, you could do the same thing. I just put something together with phoslog because that's less, it's newer, and alum used to be not really favored, still is not favored in Canada. So the difference between phoslog and lanthanum, phoslog and alum is actually that the phosphorus absorbing agent, which is lanthanum, is in a clay and which goes down to the sediment, and there it intercepts the phosphorus that is being released. It will also absorb phosphate, free phosphate like SOP in the water column, but it will not coagulate like aluminum does in the water column. It will not clean up or clear out the water right away. However, that means its effect is directly on the sediment release. And if there's any chlorophyll decrease or cyano decrease, then it is due to the effect on sediment release abatement. Here's an example of a lake in Germany, a small lake, and this was the chlorophyll concentrations before the treatment, and then they did 3 treatments in 3 years. 2007. Oh, this is in the way, isn't it? Oh well. I don't know how it.
No, it looks good. It looks
yeah,
good.
you can still.
It's good.
Can you see?
You can see it.
You see the whole title. Okay,
yeah.
good.
Yeah.
I have something weird going on there. You see how the chlorophyll concentration decreased with this phoslog treatment, and it was correlated to the phosphorus concentration, mean annual phosphorus concentration, mean annual chlorophyll. So before the chlorophyll was high and phosphorus was high, then the first treatment, it was getting lower, then it was lower, then it was not low enough for the people who wanted it very low. And so they did more treatments and it got lower yet. They wanted mesotrophic conditions, I think, or they had a certain threshold they needed. Another application was in Henderson Lake. You know Henderson Lake in Lethbridge. The probably was hyper-eutrophic, but the phosphorus concentrations are not completely, the pre-concentrations are not necessarily exactly correct. Internal load was modeled to be 50% of total load, and it was sometimes anoxic above sediment, but you also had geese, waterfowl. The total phosphorus after the treatment was here, with time decreased over the summer. This is one summer of after the application, and it was pretty low, and the next following summer it was low again. This was how the treatment was added. And so the phosphorus concentration was definitely fine. The question is exactly how much was it before, but it was very low. And what the staff, Lethbridge staff, was all excited. They dug into the photos and showed us the pre-treatment photos, same date basically as afterwards, and they said it's just wonderful how clear the lake now is. So it seems that apparent transparency in secondary definitely increased, even if we don't know exactly what happened to the phosphorus because of the bad phosphorus data before. Which is then another reason to think that internal load has a lot to do with cyanobacteria. And now I want to talk about the recent cyano increases in nutrient-poor but developed lakes and in catchments recovering from acid exposure. And that's a long story, so I will only show you a tiny little bit. In Ontario lakes, since about 1904, it has been shown that these cottage lakes, where people go to have nice clear swims and drink from the water, had cyanobacteria, are having cyanobacteria blooms. In one of the lakes where a lake association asked me to help them to do something about, it was even detectable. The toxins was detectable, although it was way below the drinking water guideline, but you know, it was going there. And further, another lake association got me involved by looking at acid-stressed lakes in the Sudbury area, where lakes had been so toxic because of low pH and also heavy metals that there were barely any fish, and the secondary was very deep. It was very clear, and all of a sudden they got eutrophic. They got signs of eutrophication. What happened there is, and if people want to know more about it, they might want to look at some references here. What happens in these lakes that used to be acidic, and also other lakes that are on the Precambrian shield, I think is the following. First, you have the lakes are acidic because of acid rain or former mining impact, and they're not developed. So you barely have any phosphorus coming in because aluminum in the terrestrial surrounding area absorbs the phosphorus. So there's basically no phosphate coming in except for precipitation. Then you have development happening and you have some phosphorus coming in. However, because of the past with a lot of aluminum going into the sediment, the aluminum in the sediment keeps the phosphorus from leaving the sediment, even when you have anoxic conditions. And that could be proven with sediment concentrations of different fractions of aluminum, iron, and so on. And then you have the third development here, where you have less acid rain now, and or you are restoring the acid former mining area, which is done in Sudbury, and you have all the external loading coming in because the aluminum is complexing with other things under higher pHs. And then you have actually now enough settled phosphorus from these occasions, and you have different conditions. You have less aluminum that can absorb all the phosphorus, and you have internal load. And that's when you have then the blooms. And now to the last possible, one of the last support of hypothesis. I always like this in a way, because in all the studies that people asked me to help them, so all the studies that I was commissioned, I was commissioned because of blooms, of cyanobacteria blooms. And at the beginning, I thought, oh my God, I'm a phosphorus person. What have the blooms to have to do? What can I do for them, for these lakes? And it turned out they were anoxic. And if I look closer, they had internal load. Actually, in all of the lakes, I looked over again when I made the slide a year ago. And so these were 36 lakes, many were polymictic, they were large and small, 5 reservoirs, 2 river systems. And there is a lot of evidence throughout the world, and they are documented by literature of large lakes and smaller lakes that really support the hypothesis that internal load drives cyanobacteria, at least in addition to other external loads. Recent increases in bloom frequency may be caused by increases in internal load due to climate change. Well, this is kind of first based on theory, and it gets more and more, I feel more and more evidence that I think it's really there. The cyanobacteria are not only affected by increasing temperature, better light conditions, more water stability, but also by increased access to phosphate. Now that's well known. The nutrients and the main nutrients is phosphate. Nitrogen also plays a role, but I'm not going into that now. Climate change, earlier stratification, later mixing, longer stratification, and increased period of partial mixing, thermocline erosion, increased all this, increased internal load and increased the amount of phosphorus that actually gets mixed and available to cyanobacteria. And the lakes recovering from acid deposition shows signs of eutrophication and cyanobacteria blooms. They're caused by increasing internal load, which is not necessarily due to climate, not necessarily to climate change, but I think that in relationship with the climate change, this is not still exacerbated. One example I thought to show is the study by Liz Favreau, who incidentally is our regional director for Eastern Canada. And she showed, this is an Algonquin Park lake. People know Algonquin Park for clear lakes where they paddle. This lake is not even close to the highway that goes through it. And it had blooms since 2007, I think. But this is now shown here. So she compared climate change data with becoming anoxic data that she used, that she determined from paleolimnology, sediment coring, and studies. So she discovered that air temperatures increasing, summer wind speed decreasing, stratification increased, and more ice-free days. At the same time, eutrophication did not increase in terms of total phosphorus because it actually decreased from 13 to 10 micron per liter. So that could not be just the total phosphorus effect. But so she concludes that internal load probably is the reason. Prolonged, stiller, and warmer ice-free season, increased hyperlimnet anoxia so that internal load, and I quote, may have fueled the algae blooms in this remote lake. And in 2012 already, this is an excellent summary of what the climate and eutrophication effects on cyanobacteria blooms might be. And I always show this because people might be interested in seeing it. It's not explicitly said that internal load has an effect, but it's very much has everything in increasing temperatures, increasing acidification, and so on. So of course, there are additional influences on the blooms and the increase of blooms. And but some of them actually might not be distinguishable from internal load. For example, iron limitation as one hypothesis that iron is simultaneously because more lakes are anoxic, more iron gets released and more cyanobacteria can thrive on iron. Well, at the same time, phosphorus is released. So how can it be, it might have been phosphorus too, the internal load. And zebra mussels, the increased organic settling on sediment, yes, but it also increased the sediment oxygen demand, and that would increase the anoxic factor, the anoxia, the area that can release, and an increased internal load. And so the last slide here, I want to just summarize then. Internal phosphorus load can fertilize cyanobacteria in stratified and polymictic lakes of all trophic states. Increasing reports of false cyanobacteria blooms in Ontario lakes, on the Precambrian Shield, and in acid-stressed nutrient-poor lakes all indicate that. Increasing internal load expected because of climate change, and that's the real bummer. Recent increases in HARPS during acid recovery are partially due to internal load, and the determination of causes of HARPS helps determine management options. Now that is important because we want to treat the cause and not the symptoms. So lake treatments that diminish internal load from the sediment support cyanobacteria bloom abatement. And thank you very much.
Great, thank you so much. So we have a lot of great questions that came in, and I'll help facilitate those for you. So our first one is from Nadine, and she asks, how confounded does the chlorophyll A total phosphorus relationship get? Because part of the total phosphorus comes from algae.
Yeah, if you calculate it out, how much phosphorus would it be? It might have something in hypereutrophic lakes, but in general, it's not an argument to think that the phosphorus that actually constitutes the algae.
So I think on my screen it's frozen. Caleb, is yours frozen too? Okay.
Would create such a relation.
Oh, we lost you for a second there, Gertrude. I think you were saying that the total phosphorus in the algae on most lakes wouldn't constitute a huge proportion of the total.
Sorry. Yeah, I mean, the phosphorus chlorophyll relationship. I think it has been shown that it would not be enough to support the content of algae, or phosphorus in algae would not be enough to produce such a relationship. I think it has been shown.
Okay, great.
I don't know more.
Okay. Another question here from AJ. Have you worked with any situations where mid-season vegetation senescence was a large enough contributor to summer phosphorus to manage? I'm thinking about curly leaf pondweed senescence in midsummer. How did you model this TP flux?
Yeah, if there is, I would say, I usually say if there's more than 25% cover of macrophytes, then I would start worrying about it and modeling it. But I haven't encountered a lake like that. I know from the literature, there used to be Lake Wingar. That's one of the old Carpenter studies in the 90s. It's the only one where somebody did a phosphorus budget and could show that the macrophytes are a real problem. I'm sure there might be some studies now in China from Chinese large lakes and so on.
Yeah,
I haven't encountered it myself.
right. A couple of questions came in directly through the chat. I'll just jump to those. Are you aware of any other binder like lanthanum that makes an inert product like rhabdophane?
That is lanthanum. Lanthanum makes rhabdophane.
Are you aware of any other binder like that? I think it's the
question. Like that. There are some new ones out, but I don't think it's like this is rare earth lanthanum. There's zeolite, but zeolite is more like a clay type or chitin containing thing. No, certainly not as easy available. There is a lot of experimental material in China, in Chinese literature, I mean, English literature. And there are some where they use, for example, sludge and stuff like that. But that's basically just iron or aluminum that was used in the waste treatment plants. And then you use the sludge, clean it up or change it a little bit and so on. I don't know of any other session, no.
Okay. A couple of questions from Dorta. She is wondering, in your experience, how important is under ice internal load compared to open water internal load?
Well, it's usually much less because of the temperature changes, difference. There are hyper-eutrophic lakes where you actually have data. I mean, where I know people studied and there are data and that show internal load is there. However, it is possible and some of it is there and it would give a start in the spring as soon as there's ice out. So there's some European lakes also where some of the early summer blooms are attributed to spring turnover. If you look closely, the previous winter had internal loading.
She has a second question here, which is it possible to predict future changes in lake internal load based on climate change predictions?
Yeah, they will get worse, right? Get bigger. In general, yes. The climate change would create more, it's complicated, of course. The air temperature increase would increase the surface temperature in lakes. At the same time, it has earlier ice out. That's why it has also earlier ice out. Now, earlier ice out could mean in a deep lake that a fast or spring turnover traps the colder water in the bottom. So the bottom water becomes colder. That has been shown in some situations too. So which in a way would say, okay, that's less release rate, less anoxia because it's dependent on temperature. But it's often that it's longer. The ice in is later. So internal load or release has a longer time to happen. And so overall, I think, and that's what people seem to suggest, the conditions are getting worse, better for internal loading and worse for preventing it to get into the lake and create cyanobacteria blooms.
There's still a few questions here, and our second session is actually shorter today, so we'll just see how many more of these we can get to, if you don't mind, Gertrude.
Okay, no, that's good. I was worried about the time a
No,
bit, but
no,
then good.
I stole time from you in the beginning, so
Yeah, I noticed. So I thought.
I'll make sure we get to as many of these questions as we can here. So there's another one that says, any thoughts and or data on what is natural or background internal loading and how we can incorporate those values into management strategies or understanding of how our Alberta lakes behave?
Yeah, that's a tricky question, I find, because what is background really? No? They have this conversation a lot in Europe because they want to, a natural state. It's all the what the restoration attempts are supposed to do. For example, the Ontario cottage model says the original state would be, they calculated out basically on natural sources. Internal load under natural conditions, it can occur in geological situations where you have relatively high phosphorus as background, which is like in Colorado, in some the higher mountains in Colorado, as I understand, but also even in things like just the St. Lawrence Basin. So I mean, it's kind of an anthropogenic point of view to say is it natural or not. It just means before we were doing something or not. I'm not sure if I want to go there. I personally like a lake that is clear and I can swim in, so it doesn't matter where it's coming from. If it was like that before, we cannot probably get it that way if we are in a geologically enriched area. I don't know if I make any sense here, but
no, I think people are thinking about Alberta lakes probably having some background level of loading because we're geologically enriched, right? And so they're wondering from a management perspective, how do you set your objectives if you expect a natural
right. Yeah, that's a good point. Yeah. Well, sometimes I'm just pragmatic and say, let's do as much as we can. On the other hand, it is good to hang up the thing very high. Otherwise, nobody wants to spend any money to get there. So
yeah,
it's not a limnological question.
So there's a question from Dawn, and it says that your hypothesis does not seem to recognize the transfer of phosphorus through resuspension of bottom detrital material for shallow lakes. Talking about, if a lake is shallow with large fetch, there's probably a lot of resuspension. Could that be part of the model of internal loading in shallow lakes?
First of all, resuspension, it depends. It can work both ways. In an oligotrophic lake, it shows that the shoreline phosphorus concentration is so low in the sediments of these lakes that they actually absorb phosphorus. And iron is high, like in Algonquin Park lakes. So in situations like Lake Winnipeg, I think that resuspension definitely increases the internal load. And it is because, as I see it, because there is pore water. I mean, the sediment pore water, the water content of the sediment, is the first step where the phosphorus gets released to from the iron oxides, and then from the pore water it goes into the lake water, in the bottom water. So if you have an enriched hypereutrophic sediment like in Lake Winnipeg, the pore water will be full of it, full of phosphorus, and any suspension will mix it. So the active area model takes care of that. In other words, to model internal load by a release rate timed and the product with the anoxic factor, where the anoxic factor is predicted from phosphorus and morphometry. This predicted this active area model, basically, it is to be taken care of that. And there is I have a paper written by Tamay Rock and myself on that. I can send it. She did some studies to compare this with and so on.
I'll just ask one more question, maybe, and then at the end I'll get you to put maybe your contact information up if it was on one of the slides, and folks can follow up if they want to on some of these unanswered questions. There is a question about what % of groundwater contribution as an internal load for phosphorus enrichment compared to other factors. Do you collect information about surface water, groundwater interactions that can help to confirm if groundwater is contributing?
That's in an ideal world, I would do this, yes. As it is, my first question is would groundwater be a problem? What is the quantity of groundwater as such? And to make maybe an estimate if it would create a lot of a problem. Usually, to be frank, groundwater is a pain to find out about, because people do not want to spend time and money in putting in measuring devices. So if I'm lucky, I go to a hydrologist just to find out about the groundwater as such, and then I think about the geography and if it could be high in phosphorus or not. So to make a long story short, no, usually not. But it's well understood, yeah. And I'm sure sometimes it seems that the budget just doesn't work, and that would be an indication to go further. I have one study in Urban Lake there where I would say I keep asking people to to spend some money on groundwater.
Great. I don't know if you had your contact. Oh, there it is. Perfect. Look at that.
I forgot to, yeah.
Yeah, right there. So if anyone wants to follow up, I know we didn't get to everybody's questions today. I encourage you to reach out to Gertrud at her email on the screen there, and we can put it in the chat box later as well, if you'd like to access it that way. So again, thank you so much, Gertrud, for being flexible with this presentation. Folks don't know you've basically been away for the past month, and you were so generous to join us on our last session here today. So thank you again.
Yeah, thanks for the invitation. It was fun. And good luck for the next.
Thank you. Yeah, I invite you to stick around and watch the next session if you'd like to.
Yes,
Great.
sure.
Great. And
I will stop sharing my screen. Hold on.
I think I can do it here, maybe.
Oh, yeah.
There we go.
Okay, good. Perfect.
Perfect. Okay, so for our next session, we originally had a spatial data scientist who is going to join us. Unfortunately, at the last minute, they had to back out. And so I'm really, really appreciative that Caleb has saved the day and is going to present on the same subject. Caleb is not a spatial data scientist, but he's been coordinating various aspects of this project and knows it very well. So I think Caleb will be able to give us a great overview of this project. It will be maybe a bit shorter than the original presentation, but that'll just leave lots of time for questions, of course. So Caleb, I'll let you share your screen.
Great. Just want to check that you can hear me okay, that I'm loud enough.
Yeah, sounds good.
Okay, so I'll just share my screen. And you can see that okay?
Yep, looks
Okay,
great.
Great. All right, thanks, Brad. Yeah, kind of like Brad said, it was going to be somebody else presenting on this topic today, and I was really excited to see what they were going to say, but I'll do my best to relay what this project is and what we're working towards. And oops, before I get started, I just want to say that some of the slide content has been adapted by a presentation from Evan Delancey, that geospatial analyst from the ABMI. So I'm grateful to him for sharing his slides and for allowing me to be able to share some of the information from that presentation in this presentation today. So just to kind of give a background on this project, the project is using satellite imagery to learn more about algal blooms and cyanobacteria blooms on Alberta lakes. Originally, the project came out of technical advisory committee meetings with the Pigeon Lake Watershed Association. So this technical advisory committee and the PLWA in general have been really active in working together to learn more about Pigeon Lake, which has had a history of blooms in recent times, and have been working really closely with Dr. Rolf Feinbruck at the U of A, some scientists at Alberta Environment and Parks, and us at ALMS to learn more about their lake. And in one of these meetings, it was brought up that perhaps satellite imagery could be used to learn more about the cyanobacterial bloom dynamics. And subsequently, the ABMI was brought into this, Evan Delancey, because of their geospatial expertise. So that was the original purpose, but now has been expanded. So, and I'm going to get more into what it looked like at Pigeon Lake in particular, but just to kind of say that the project has expanded significantly recently, and now we've brought in partners such as Lac-La-Biche County, let's just say Watershed Council, the Wabamun Watershed Management Council, and other field staff at Alberta Environment and Parks to develop this project, and to further some of the goals of the project beyond Pigeon Lake necessarily, but also to develop satellite metrics for algal blooms on lakes across Alberta. Also working with these partners to use in situ samples to validate and calibrate the imagery and the satellite data that we're using to estimate the blooms. And also other goals include using not just chlorophyll A, which is kind of the standard pigment that's been used to understand blooms, but to go beyond to other pigments that are more definitive of cyanobacteria and even other kinds of algae. And also one of the goals is to use historical data to track some of the historical trends in these blooms. So this project is really reliant on Earth observation satellite data, which comes in a lot of different forms. A lot of different organizations have satellites that you can use data for understanding what's going on in aquatic systems. For this project, we're using satellite constellations that are managed by the European Space Agency, specifically the Copernicus program. And there are multiple satellites that are part of this program, but the Sentinel-2 and Sentinel-3 satellites are the most useful for water quality. And to my understanding, it's because of the bands, the acquisition bands that the satellites are configured to, and what these bands can tell us about different things in aquatic systems. And all of this data is conveniently freely available through Google Earth Engine, which hosts the data and allows users, and kind of has a platform to allow users to process and visualize the satellite data. So why use satellite and Earth observation data? I guess for this project in particular, it's because it's a really great and one of the best approximations of surface cyanobacteria or algae levels that we have, because it gives a really practical picture of the spatial distribution of blooms. I guess compare that to how we sample lakes on the water generally through some of our major programs, in that we try to get an estimate of a lot of different parameters across the lake by doing composites at 10, maybe 15, 20 sites, depending on the lake. For our Lake Watch program, we do a 10-point composite. But satellite acquisition is so much more powerful because you can get as many data points as you have pixels on the surface of the lake, and that just is a better approximation of how heterogeneous the bloom can be across the lake. And because of that type of data, we can develop different metrics and really consistent metrics for understanding how the blooms are changing within a season and between years as well. Satellites are really powerful because of their high sample rate. I'll go into this a bit later, but through the Sentinel program, the sampling, the acquisition schedule means that lakes in Alberta are visualized every 1 to 5 days, depending on the satellite. Because the Copernicus Sentinel data is freely available, it's extremely low cost to do this type of monitoring. And it's passive, which means we don't necessarily need anybody to be on the water except for the validation the process. And there's a lot of data that you can get from satellite imagery, and some satellites such as Landsat have quite a long history of data acquisition as well. I think some of the Landsat satellites go back to the 80s. It's also worthwhile to understand the limitations of using satellite imagery. So one thing that I think about a lot is the cloud conditions, because Alm's contribution to this project is doing the field work. So we're always checking the cloud forecast, and you need cloud-free days to be able to get worthwhile imagery to estimate the surface levels of blooms. Water turbidity and atmospheric conditions can also impact satellite estimates. As far as the techniques and the models that are used to translate the imagery into actual pigment concentrations, the techniques are relatively new. I would say for lake algae and cyanobacteria, I think it's much more developed for oceans, but for lakes, it's relatively new, and the application is still fairly limited. Another limitation is that you need to do a lot of groundwork beforehand to get a really accurate and validated model, and that the imagery is only really estimating surface levels, and that you kind of need to understand that when you're comparing maybe the data to other sampling programs, such as standard programs, which oftentimes integrate chlorophyll levels from the surface down to different depths, euphotic depth, or sometimes the thermocline. Another limitation is possibly defining the bloom standard. So I'll get into this a bit later, but depending on your lake system and the geography, different lakes may have different levels of what a bloom might be. Say in Ontario, they would say a lake is blooming at much lower levels of chlorophyll, where in Alberta, where we have much more enriched sediments and yeah, just our geography kind of means we have a bit more eutrophic lakes. There can be kind of a difficulty in understanding what is a bloom for your system. I kind of talked about this a little bit earlier, but right now, most of these models are limited to chlorophyll A, which is a proxy for all phytoplankton, and that usually we're interested in cyanobacterial blooms, but that chlorophyll also estimates true algae as well, not just cyanobacteria, but all phytoplankton in the water column. And another thing that I'll mention is that this type of approach for monitoring doesn't replace traditional lake sampling because it only really captures those chlorophyll levels and doesn't allow you to relate them to nutrients, which we're just talking a lot about, and that it really complements other lake monitoring programs, but it shouldn't really replace them because it's limited in the type of information that it gets. So to start off, coming kind of back to the work that was done with the PLWA and that technical advisory council, the first step was to start to characterize satellite-derived chlorophyll A values at Pigeon Lake. And the two satellites that were used for this purpose were Sentinel-3, which has a daily flyover of Alberta, has a really wide swath, so it captures lakes in Alberta every single day. It has a 300-meter pixel size, which I would say for the size of our lakes is relatively low. So that limits using Sentinel-3 for fairly large lakes by Alberta standards, and as well lakes that don't have complex shoreline morphometry, or maybe islands as well as another consideration. The other satellite that is used that it's probably better for Alberta lakes is Sentinel-2 because it has much higher spatial resolution, has a 20-meter pixel size. But another bit of a drawback compared to Sentinel-3 is that it has a flyover only every 3 to 5 days. So you have a lot less data to work with, but you have much better spatial resolution for Sentinel-2. So these are some of the images that the ABMI put together looking at some of the bloom values or chlorophyll values for Pigeon Lake. So that initial approach used algorithms developed for lakes in Ohio and Estonia. And there was a bit of a concern that some of the levels developed or calculated from those algorithms might actually be misrepresenting the actual chlorophyll A levels at Pigeon Lake, since Pigeon Lake is quite different from the lake types in Ohio and Estonia. So the next step was to validate a model for Pigeon Lake using ground truth and ground truth samples. So that is what we did last year. So last year we worked with the PLWA and some really great volunteers. I think Bob Gibbs is on the call today, and he put in a lot of work last year with us at ALMS to do this ground validation at Pigeon Lake. So that involved sampling the lake on the exact days that the Sentinel-2 satellite went over, and we needed a cloud-free day and a day where the wind levels were low so that it was safe to sample. And the information or the samples that we collected on the lake were a surface grab sample that we used for pigment analysis. It's done at Dr. Weinberg's lab. So that sample gets concentrations of chlorophyll and also other pigments of interest. Another sample is collected that is used for phytoplankton enumeration and identification. And then supplementary data is also collected, such as Secchi depth, water depth, wave height, and of course the GPS coordinates so that we can relate the location of that ground truth sample with the pixel visualized or captured by the satellites. And this was done at 20 sites across Pigeon Lake within the pelagic zone. So kind of in that area of the lake where it's, I think we estimated it was deeper than about 4 meters. So we did that 5 times, and these images show all of those days where the sampling occurred. We're actually very, very lucky, I would say, that we got so many days that had very low cloud cover. Doing this project now for 2 years, it's extremely difficult to get cloud-free days. So based off of the samples that were collected, about 80 of the locations had usable data because they weren't covered by clouds. And they were all coordinated with Sentinel-2 flyover days and Sentinel-3 by default, since Sentinel-3 goes over every day. And it's really interesting to kind of see just off the bat how the lake color kind of changes between June and September there, and that we kind of see really high color in that August imagery. So right away we can see that we've captured a range of values of chlorophyll, which is one of the goals to getting a good calibrated model, is to getting a large range of chlorophyll values, but then also getting the range across the season to capture seasonal variability, and then also variability across the surface of the lake by getting samples from those 20 different sites. So this is what it looks like to compare what the concentration of chlorophyll from those surface grab samples versus the spectral index that approximates chlorophyll A from the satellite. I think this is just for Sentinel-2. So this is a figure that Evan produced to demonstrate that the spectral index that estimates chlorophyll versus the actual chlorophyll values actually has a very strong relationship, and thus we could actually get a good validated model. And I just added a 80 microgram per liter line there just to demonstrate that for the model we don't actually specify values of chlorophyll above 80, and that you'll see later on our visualization tool kind of maxes out at 80 and says that it defines a certain color for values above 80, and we can kind of see that there aren't a lot of data points really above that 80 microgram per liter point. So I think that that's really fair. So this is some of the first images that were shared with us that uses this Pigeon validated model to assign chlorophyll A values for every pixel. And we this was done for both Sentinel-2 and Sentinel-3. And right now the tool visualizes data for from 2017 to 2020, and 2021 is also within the tool, but hasn't had the cloud masking or data processing done. So it still integrates a lot of images that have clouds in them. And I don't do that work specifically, but I know that it takes a lot of work to try to factor out the cloud interferences from the imagery. So the preliminary visualization tool is still under development. Currently, it's not publicly available, but the goal is to make it publicly available. So we're working closely with the ABMI, Dr. Rolf Feinbruck, the PLWA, and other partners to develop what this tool will be, what it looks like, how people can interact with it. So that takes quite a bit of time, but the goal is to eventually have it publicly available. And it allows users to interact with the satellite-derived chlorophyll A levels at Pigeon Lake using the Sentinel-2 and Sentinel-3 imagery. And it actually is near real time because the way that the visualization tool is set up, it's set up through Google Earth Engine, which integrates the satellite imagery from Sentinel-2 and Sentinel-3 between 1 and I would say like 4 or 5 days. So it actually is near real time, which is really exciting in terms of being able to see how the bloom progresses through the season in near real time. So I'm just gonna exit out of my presentation now, and I'm gonna go to my browser and give a little demo of the tool. So I hope everybody can see this. So on the left side, we have our selection panel, which you can use to select which dates you want to have visualized. So right now I have loaded up all of 2020 because 2020 has pretty interesting imagery. And you can also select whether you want chlorophyll A or the lake's true color. And then you can also select the satellite as well. So Sentinel-2 or Sentinel-3. And I have Sentinel-2 loaded up, which is that satellite that has that high spatial resolution, but low temporal resolution. It doesn't fly over that often or as often as Sentinel-3. And then once you hit go, it takes a little while to load up all of the imagery because it's not immediately available. It has to pull it from the Google Earth Engine catalog. So I've already loaded up all of 2020. And at the bottom left, I'll just point out the chlorophyll scale. So it goes from 0 to 80 micrograms per liter, or 80 and above. And this top pane you can use to navigate the different images, different days of collection. So this one starts in May, and I'll just click through, go through the different months. Now we're in July, and you can kind of see that the tool is starting to visualize some higher chlorophyll levels in the lake. This is the end of July. And now once we get into August, you can see that the levels have gotten really high from being on the lake around this time. In that northwest section of the lake, that yellow color being 80 micrograms per liter or higher would translate into, say, surface scum type conditions. So it's really, really high cyanobacterial biomass in that portion of the lake. But the tool is doing a really good job of demonstrating that that is not the conditions across the whole lake, and that as we kind of click through different days, we can see how the bloom changes and what some of the dynamics are and how they may be related to wind events and other kind of mixing events as well. I think this one does a good job of showing possibly what westerly wind is doing. And I'll also just mention that this imagery represents what the lake looked like at around 1 in the afternoon. That's when the flyover for that part of the province is. And now as we're getting into September, the bloom you can kind of see is still fairly prevalent across the surface of the lake, but that it is moving to different regions. And then by October here, it's starting to dissipate, and that's the last image that we have. So that's kind of what the tool is designed to do, is to look through the different images here and to be able to interact with them. And one of another feature that the tool currently has is estimating the mean or average chlorophyll A across the lake for each of these dates. So you can kind of see from a lake's across the whole lake what the average chlorophyll is. And I'm going to go back to my presentation now, and just go to the next slide and show that when you get the tool to upload all imagery available from 2017 to 2020, you can start to compare the years and how the blooms have kind of progressed from a lake-wide view. So 2020, which we were looking at, is that kind of like blue-green color. You can see that the mean chlorophyll happened, the max happened a little bit earlier than other years. So we can start to kind of ask some of these questions. How are the blooms kind of varying year to year? And we can see that 2019 was a pretty low year for chlorophyll, and our lake sampling data also confirms that 2019 wasn't so bad in terms of blooms. So this is what the tool is designed to do, is to start to kind of address some of these questions. All right, so now beyond that, so we had developed that tool and we used surface validated samples to increase our confidence and calibrate the imagery. So the next steps then for us were to further develop the tool to include additional metrics. So in more than just the average level of chlorophyll across the lake, you can start to develop other metrics, such as how large is the bloom if you define the bloom flag, or what you would say, what concentration relates to a bloom. And you can start to develop metrics around the intensity or severity of the bloom as well, which I'll get into a little bit later. We also want to continue to develop the aesthetic of the tool to make it much better in that respect. The other next step is to explore additional data, such as all those phytoplankton, preserved phytoplankton samples that we have, to kind of relate perhaps the chlorophyll concentrations and other pigment data that we get to what species are actually prevalent. And another next step is to validate the tool and develop our understanding of these bloom dynamics at other lakes in Alberta. So I'll get into that a little bit later, but I want to just kind of expand a bit on that development of the tool. So as I kind of said earlier, the application of this sort of monitoring is fairly limited, but there is precedent in Canada already. So Environment Climate Change Canada has been delivering their EO Lake Watch program for a number of years now, and they use this this tool to visualize chlorophyll A levels of the surface of Lake Winnipeg, Lake of the Woods, and Lake Erie. So those are the lakes that they have as part of this program. And they only use Sentinel-3 data currently. And one thing that we like about this is if you go onto the website and you go to their tool, they have a really great layout of how to explore historical data. So for this Lake Winnipeg screenshot here, you can see this is the bloom extent. So how large the bloom was based off of the surface area of the pixels that are above 10 micrograms per liter. You can see how the bloom extent varies from year to year. So we really like that. They also do a really great job of integrating other metrics, such as intensity, which is defined as the average chlorophyll A measured within a total area of the bloom flag. In their case is 10 micrograms per liter. They used extent, which I just talked about, and severity, which is actually the product of extent and intensity. It kind of integrates the two to approximate the overall severity, how intense the bloom was across the lake and within a given area. One thing that this tool does as well is to do multi-day averages of chlorophyll A, which our tool currently doesn't do, but I think would be really useful for Sentinel-3, where you're getting those daily levels. And I think they do it as well to kind of factor out, I think, some of the cloud interferences. So it's something that would be interesting to pursue. Something that this tool does really well is to contextualize near real-time results. So if you're part of their email notification list, I get emails, I think, weekly about Lake of the Woods, Lake Erie, and Lake Winnipeg, and the bottom right kind of shows what's in the email. So I really like that they contextualize how the current bloom is progressing compared to historical data. So it shows the median between, in this case, between 2002 and 2020, and then the 25th and 75th percentiles, and the red line is 2021. So for Lake of the Woods, it's kind of following what you would expect, but on actually a little bit lower than the median since 2002. So I really like this approach for understanding right now what are some of the real-time, how does the real-time results kind of contextualize with the historical bloom data for this lake. So really like that part of this project as well, and would be something neat to work towards for our project. And we have actually been able to explore some of these additional metrics and capabilities of this type of tool through a SAIT student project. So Evan worked with a class at SAIT, geospatial program class, to sort of begin to explore what these metrics would look like for Pigeon Lake. So they started out by investigating bloom severity, which we can see it was calculated for the Pigeon Lake data using Sentinel-2 and Sentinel-3. And again, that's the sum or the product of intensity and extent. And they also use the imagery and the tool to sort of explore where the chlorophyll A concentration is the most intense in the historical record, and using the imagery from Sentinel-2 and Sentinel-3 on the right side of the screen here, it's helping us understand that the bloom seems to be the most prolific in this time period in the northwest region of the lake. So yeah, it was really great to work with the students in this project to develop some of these metrics and to see what they were able to do in a short period of time. And we look forward to kind of developing some more of these metrics as well, possibly working with SAIT students in the future. All right, so the other project next step that I'm going to go into a little bit more is what we've done to validate the tool and develop it for other lakes in the province. So we continued the validation fieldwork in 2021. And the reason for this is we have a good tool for Pigeon Lake, but one of the questions is, is the tool specific only to Pigeon Lake? Can we start to apply this tool that's been validated at Pigeon Lake to other lakes in the province? And one way to sort of address this question is to develop other tools at other lakes in the province, and then to maybe compare how these models are between the lakes to sort of learn if we could use the model to get these chlorophyll A surface estimations for any lake in Alberta, regardless of if they're validated, or if the best approach is to validate the lake before developing a visualization tool for the lake. So the 3 lakes that we did this validation, the sampling at this last summer, were Lac La Biche, which is the top left, Abatement top right, and Lesser Slave Lake on the bottom. So these are also fairly large lakes from Alberta standards. They're interesting because they have different cyanobacterial community and species abundances. They're all very popular recreational lakes, and they have histories of blooms, albeit differing, maybe severities of blooms. And they also have invested stewardship groups and also partners that are invested in learning more about the lakes, and thus we had lots of fieldwork capabilities for these specific lakes. So for Abatement and for Lac La Biche, we were able to do sampling to validate Sentinel-2 and Sentinel-3. But for Lesser Slave Lake, for logistical constraints, the goal was to validate Sentinel-3 imagery only. And I need to give a really big shout out to our partners who assisted in this work. Lac La Biche County staff went out quite a bit this last summer, had a lot of difficulties finding good days to sample. When you work with lakes that are that large, you need to be really careful about the wind levels. So we had a lot of days where, it's the morning of, we're trying to decide if it's going to be safe enough to sample and if it's going to be cloud-free enough. So big shout out to Lac La Biche County for all of their hard work in this regard. Abatement Watershed Management Council, thanks Stan Franklin's on the call today. Big shout out to him for being able to go out 3 times on Abatement and go to 35 sites across the lake. Long day, but we had a really great time sampling with him and the WWMC group. It's really great to work with. And at Lesser Slave Lake, the sampling was delivered by Alberta Environment and Park staff that were sampling the lake, doing standard sampling, and were willing to do this validation sampling as well when they were on the water. And when sampling events were too cloudy, we reached out to the Lesser Slave Watershed Council, and they were able to do some validation sampling as well at the one of the basins at Lesser Slave Lake. So thanks to all of the partners for being part of this project and supporting the fieldwork portion. If you want to learn more about how the sampling went, I talked about that last week. So you can check out the YouTube video from our last week's webinar. But that's all I have. And if you have any questions for me, I'd be happy to take them now. If they are more geospatial specific questions, I have shared Evan Delancey's email on this slide. So yeah, I'm happy to take questions now.
Sure. So there is a question here I think you can probably answer, which is, why did you choose locations deeper than 4 meters?
Yeah, that's a good question. And that's because we have explored this question quite a bit, but we haven't got a great answer for it. But one of the questions is that we don't know how deep in the water column the imagery actually penetrates. So one of the fears with, say, validating locations that are too shallow is that the chlorophyll values that we're getting for the surface of the lake might actually be different from what the satellite is approximating, because it could be approximating chlorophyll values for macrophytes that are growing there, or even benthic algae. So for that reason, I didn't like point this out, but for the Sentinel-3 tool, we actually have added a bit of a buffer between the shoreline and the lake to be able to eliminate some of those interferences. But even so, if I maybe go back to an earlier slide that shows Pigeon Lake, I don't know if it's going to show it. I think I have to go. I think this is worth showing. And that's that there are still shallow areas of the lake that are given higher levels of chlorophyll than you would expect. So I don't know if you can see my mouse, but in the southeast part of the lake, there are some, in this imagery anyways, you can kind of see that possibly the chlorophyll A levels are a bit higher. There's a bit of a area of pixels here that look higher. These are actually just more shallow areas of the lake, and we know that by looking at the bathymetry. So when we're selecting site locations, we want to validate pelagic locations where the chlorophyll is just the contribution is from phytoplankton and not from benthic algae or macrophytes.
Great. There is a question asking about you, rather than using a satellite, could the data be sent via cell towers? And I wonder if, I think maybe it's just, I'm not sure if we'll be able to answer the question, because the data that's coming through the satellites is actual imagery that the satellites themselves are collecting. But maybe if you want to send in a refinement to the question, I'm probably misinterpreting it. Go for it, and we'll try our best to answer that, unless you want to add anything there, Caleb.
Yeah, I think, yeah, just to kind of reiterate Brad's point, we're getting the data is being collected by the satellites. Yeah, so feel free to expand on the question a little bit if we haven't answered it.
Here's a question that says, did you consider adding a third dimension, depth, in the matrix when mapping/sampling bacterial growth, which is an important factor? Can you infer depth information using European satellites? Can LiDAR help to map depth contours for bacterial extent?
Yeah, that's an interesting question. I definitely thought of using satellite imagery to learn more about lake bathymetry, because lots of the bathymetry that we use for sampling, the last time it was done was 60s or 70s. I am not an expert in geospatial satellite type work, but from my limited research, it's really challenging to estimate depth, because you lose a lot of light very quickly in water. But I would imagine that LiDAR would be a better approach for this. I think LiDAR works in cloud-free days, but yeah, I think I don't think that the Sentinel satellites are configured for that type of data, but that I think it would be an interesting question to look into later on, because we know from fieldwork experience that that the surface levels that we're validating and that the satellite might be capturing might not actually capture a bloom that is within the water column, say when we're thinking about metallinetic type blooms, which are much lower down in the water column. So if a satellite-based monitoring approach had that capability, I think it would enable us to start to learn more about some of these lake systems where the bloom and bacterial abundances are much lower in the water column, and still have large implications for the lake in terms of toxin levels. So I think that would be a really interesting question to explore, but I think is with outside of the scope of the Sentinel 2 and 3 capabilities.
Okay, great. We had some comments in the chat, people saying thanks for the sessions today, Brian and Nadine. Thanks for that. I just threw Gertrud's contact information into the chat, as I had promised I would do that about an hour ago. So why don't we do our draw for today? I took away my blur tool, so I think I can actually show the textbook that we're giving away today. And I'll let Caleb do the draw.
Okay, I just have to change the formula.
Oh, yes. We're using a fancy Excel formula to draw
Okay,
people.
refreshing. And the winner is Jay White.
Great. Okay, I think he'll appreciate this book. He had some good questions about internal loading in the first session. So great, we can get that to him. And yeah, thanks everyone for joining us today. I'm really pleased with how the whole webinar series has gone. Our speakers were really interesting and professional, and all of them were very happy to share their knowledge with us. Our participants were very engaged and curious and polite, and so I really, really appreciate that from everyone who attended this session and past sessions. So all of these videos are posted on our website, and they're on our YouTube page. Just a reminder that our next event will probably be our AGM, and that is scheduled for November 25th, and that is likely to be virtual. So I hope we'll see some of you folks at the AGM. Otherwise, I hope everyone has a great fall and a great Thanksgiving, and everyone stays safe and healthy over the next few months. And again, thanks, Caleb, for saving that presentation for us today. Okay, so I'll go ahead and end the session now. Thanks, everybody.